Hi there, Himanshu this side, physics faculty at AskIITians. So today we are here to discuss about the lecture number 4 of the chapter Gravitation. Now this lecture number 4 is very important and at the same time it's very interesting also. First of all, let me tell you this lecture number 4 is a part of gravitation as per your NCRT book, but this is little bit different. Right, when you look at the grade 11th book, then there is a separate chapter called gravitation, and one more chapter you will find there, the fluid dynamics. So there we are discussing about the fluid's motion, the properties related to the fluid, something called surface tension, viscosities. So these kind of terms you will be hearing there. But this chapter is very interesting because this is something new. So far we have been discussing about the solid objects. When they move, when you exert a force on them, then they will cover some certain distance. We can calculate their velocities. But here we are talking about the fluid bodies. So this is the only section in your grade 9, this today's lecture, which is related to the fluid section. Now one more chapter would be coming, something called the Bernoulli's equation and equation of continuity. There also we will have a little bit idea about Bernoulli's the fluids motion, which will be a part of work, energy and power. That also you will be doing. So these are the two chapters, these are the two sections, lectures I would say, which are dedicated for your fluids motion basically. Rest all the other chapters are mainly dedicated for the solid bodies, right? You do not have the heat in this class, in this grade basically. So, but mainly the discussion is about the solids only. Now what we do in this chapter, so in this particular session we will be talking about the pressure in the fluids, then Pascal's law, then buoyancy, then sinking and floating concept, and then variation of pressure with depth. So all these topics are very interconnected to each other. And if I say, then this is something different which you are learning in the grade 9. So far everything, whatever you have been doing, Newton's laws of motion and motion in one dimension, it was all involving the bodies of particle of mass, this. But now you will be taking the help of water every time, right? So that's a very interesting part here. So what actually this, after covering this chapter, what you would be able to understand. So let me take some examples. If somebody has gone to the car washing place, right, then you must have seen that the car is standing on one side and that guy is standing on the other side. So that guy pushes something with his legs and the car will get lifted up. And now once the car is getting lifted up, the person will go inside this area and he'll wash the car from the bottom side, right? So how is that possible? Such a heavy car he has lifted up with a very small force, just with the legs. So what makes it possible? So we'll be talking about that. Then another part is, sometimes you have seen that if you have a container which is filled with a liquid, okay. Suppose let's take an example for water. And now if you drop a wooden block, it will float on it. But at the same time, if you bring a heavy object, let's say you bring a stone or something, right? So if you bring that stone and put it inside the water, it will sink. So what is the difference between wooden block and the stone? What made it to float? What made it to sink? So what is the reason behind this? This thing also will be discussing in this chapter only. So this chapter has a many real life examples, right? So I would be talking about all of them one by one. So let us begin now. First, let us understand few laws and then we'll see how to use them in the further parts of physics. So before I go ahead, let us first of all define what is pressure. How do we define pressure in a fluid? So pressure means something which is getting pressed, right? That's called pressure. So suppose you are having the exams in the school, so you are under pressure, right? The English, physics, chemistry, maths, bio, SST, all these things are like acting like a force on you. But that is what we call a pressure, right? So pressure is basically what? Suppose let us take one area. Suppose it's a area, surface areas, any surface I'm taking, and now if somebody is exerting a force over it, So basically you are pushing it, you are pressing it, right? So this pressure is basically the force per unit area. How much force you are exerting on the total area. That's called the pressure. All right. Yes. So actually, what makes it different? The pressure, right? How, let us understand this concept of pressure. What exactly it indicates, right? So mathematically, if I say that, then the pressure would be equal to force over area. Usually, you will find this thing written, right? But this is not a complete formula. We are missing here something. Yes, pressure is force per unit area, but this force needs to be changed here. This is not the any force you can take. Suppose I have this book. Okay, now I am exerting a force on this book like this, in this way. I am exerting a force on it. So it is getting pressed. Yeah. Suppose if somebody exerts a force on the book this way, the same amount of force, it will accelerate. Yeah. So suppose you are exerting a force, let's say 10 Newton of force I'm exerting this way, it was getting pressed. But when I'm exerting the same amount of force this way, it was moving forward. So any force which you will exert on the body will produce a pressure? No, that's wrong. We cannot say like that. So what we should say? The force which is perpendicular to the surface. So I should put a perpendicular sign here. This is called a thrust, right? So any force which is acting perpendicular to the surface, that we have to take. So if the force is acting along the tangent to the surface, we should not count it as a force which will provide the pressure. Tangential forces will not provide the pressure. For this, we'll have a new term, right, which we'll be learning in the grade 11, right, in the chapter properties of matter. So right now, don't get confused. Just remember one fact, that in a pressure formula, the force which we have to write is the perpendicular to the surface. It shouldn't be the tangential to the surface. We should always write down the perpendicular force. That's it. If any force is tangentially, that would not account into the pressure. So that is what the meaning of pressure is. So pressure is basically perpendicular force. Now what is perpendicular force? The force which is perpendicular to the surface divided by area. That is what we call the pressure. So simply you can say F perpendicular over A. Now there are many examples of it. So first of all, let us try to understand the pressure concept here through this formula. So you can see this kid is sleeping here, right? And this is basically called the bed of nails. So he's sleeping here and he's not getting hurted also. Even he's smiling, right? So how is this possible? What makes it possible to sleep on the bed of nails? You must have seen it somewhere. I'm not sure, but I have seen it many times that I have seen that people are sleeping on the bed of nails and still they are not getting hurted. So how is this possible? What makes it possible, right? So actually what happens, suppose this is the bed of the nails, like this. So you must notice one thing here. They don't use 5 or 10 nails. They use around 1,000 of nails. Because if they use 5 or 10 nails, what will happen? Let's say if I use less number of nails, so the contact area would be very less, right? If somebody is using only, let's say, these many nails, now the contact area is very less, only 4 nails are there. So if contact area is very less, what will happen because of this? This term will decrease. If this term decreases, the pressure will increase. And now he'll get hurt. So what they do basically, they use more number of nails. If they use more number of nails, then contact area would increase. And if contact area increases, the pressure would decrease. So how beautiful it is, right? Similarly happens when you take a pen and now you press this pen with the nib on your finger. It's getting hurted. At the same time, if I use something else, suppose if I use my mobile phone, right? And now if I try to press my finger with the same amount of force, right? It's not that much pain I'm getting right now. So force was same, but contact area matters. So in the first case, when I was using a single nail, it was a very small size pin. So the contact area was very less and the pressure was more. Okay, so that's the meaning of pressure in a fluids. Now let us go to the Pascal's law. So what Pascal's law talks about? Suppose here you see, this is basically will make you to understand that example which I was talking about. So I was talking about one example where the car is being placed at a certain place and the person is pushing with his legs from one side and the car is getting lifted up. All right. So for that, we have to understand first of all what is Pascal's law. So what Pascal's law says, any force applied to a confined fluid. So here we can see we have the fluid here. This blue color thing is a fluid. Okay. And now you're pressing it from this side with a force F1. This is some cross-sectional area A1. All right. And this is some cross-sectional area A2. The A2 I'm keeping a little bit large because I have to place my car over there. I want to get lifted it up. Right. So what Pascal's law says that any force applied to a confined fluid in a transmitted is transmitted uniformly in all directions. So any force you apply here, right? So it will get transmitted, the pressure which will be getting produced there. So that pressure will get transmitted throughout the liquid at all the points equally. So if somebody has exerted a pressure, produce a pressure P here, then at this place, the pressure will increase by P. At this place, the pressure will increase by P. At this place, the pressure is increased by P. So any pressure you exert in one part of the liquid, it will get transmitted throughout the liquid. All right. So that is what the meaning of pressure is. All right. Basically, what does pressure signify? Pascal's law says that any pressure which you produce gets transmitted uniformly. Okay. So I have exerted a pressure of P here, which is equal to force per unit area. So the same pressure would be reaching here as well. So this must be equal to F2 over A2. Now you see this relation. F2 is equal to what? I can write it as A2 over A1 multiplied F1. Now F1 was the force which I was exerting. I was pushing it. This force is not very large. It's a very small force. Let's say I'm exerting a 10 Newton of force. But this A2 area is very large. Let's say I'm taking it to be as a 100 meters square. All right. 100 meter squares of area is there on the other side where I have to place my car. So I will be placing my car over here. Okay. And this is the place where from where I'm pushing it. And this area is very small. So let's say only 1 meter square. So now you see basically you have done the work of this much by exerting a force of 10 Newton. But on the other hand, how much force we are getting? 1000 Newton. Right. So there is nothing like the force conservation. So don't confuse with that. It's all about the pressure. The pressure would be same everywhere. Whatever pressure will produce at one place, it will get equally transmitted throughout the liquid. Hence, on both the sides, we have got the same force. Oh, sorry, same pressure, and hence we have got the more force on the other side. So hydraulic lifts and hydraulic brakes, right? These things, lifting up an object and all, these things works on the principle of Pascal's law. Okay, just remember it. Now going ahead. Now when you're talking about the pressure, let us understand one more concept here. You must have seen in some documentaries, right, that these scuba divers, when they go down in the sea, they feel very pressurized. And that's why they have to wear a special kind of suit as well, right, which will exert an outward pressure and it will make them comfortable. So why does the pressure increases as we go down the surface? What makes it possible, right? Why it is increasing the pressure? And vice versa, If you go above the Earth's surface, the pressure would decrease. So you must have heard that kind of example in the lower grades, in the grade 8 maybe, that when you go above the Earth's surface on the mountain, let's say, it's a very high mountain. So there the pressure is very less. So if the pressure is very less, then it's very hard to cook a food there, right? So that's why it is suggested to take care of that part as well. So that's why what I'm saying is basically that when we go above the Earth's surface, we have problem in breathing as well because pressure is very less. Okay, and then when we go down the Earth's surface, sea surface, basically sea level, the pressure is increasing. Now, what is the main reason? Why does it happen? So let us understand. It's very simple, not a very tough thing. I'll be using the simple Newton's laws of motion concepts here. Okay, so let us have a look on this part. This is a, let's just see, and we want to calculate the pressure at this point. Let's say that we want to calculate pressure at this point. So what I'll do, let me imagine a very small size cylindrical surface. Very thin cylindrical surface, right? It's basically, there is nothing like it. There is a cylinder I have placed. Imagination I have made in my mind that I am imagining that part of fluid which is in this cylinder. And I'll draw the free body diagram. Means I'll show all the forces acting on the cylinder. What will happen? Let us have a look. So this surface you see. Now this surface is open to the atmosphere. Right? Any surface open to the atmosphere will have the pressure equal to 1 atmospheric pressure. Because if any surface, which I'll be representing with P naught here in this derivation. So any surface which is open to the atmosphere must be exerting a must be exerting a pressure on this, right? Due to the gases which are present in the atmosphere, they are exerting a pressure on this, and that pressure is equal to 1 atm. You can measure this pressure with the barometer and all such kind of devices are available, right? So this pressure should be how much? 1 atm. So this must be exerting a certain force here. And at this place, let's say the pressure is P. So this also must be exerting a pressure like this. So it must be exerting a pressure of P. Okay. Now, that's the pressure at a H depth. So from upper side, the pressure is P naught. So what is the force? So force is nothing but pressure multiplied area. Right. So force is equal to P naught multiplied area. Similarly, if I come here, what will happen? From the bottom side, the pressure is P. So force will be pressure multiplied area. Yes. One more force must be acting on it. It's a still water, right? It's not jumping like this. I'm assuming it's a still water. So it's in equilibrium. So all the forces must be balanced. So upward forces must be equal to the downward forces. What about the other force? Yes, the gravity. The gravity must be acting in the downward direction. Gravity acting on this much part of the fluid. Okay. So what are the equations now? Upward force equal to downward force. So I can simply say that this plus mg is equal to pa. Downward force is this much, and that must be equal to pa, the upward force. Now you see here one thing. I can write it as P minus P naught A is equal to mg. Why I'm saying this? Take this on the right hand side. Pa minus P naught A. Take A common, it will become this. So P minus P naught A is equal to mg. What is m? M is the mass of this much part of fluid. Now I can write mass as density multiplied volume. That's the mass, density multiplied volume. How I can write down the volume of the cylindrical object? So volume of a cylinder is area multiplied height, pi r square h. So basically area multiplied height. Height is h. Let us put these numbers here. So P minus P naught multiplied area is equal to, in place of m, I'm going to put d, a, h, and g is already there. Area and area term will get cancelled out. So we'll get p minus p naught is equal to d, g, h. Hence p is equal to p naught plus dgh. So when you go h depth below the sea surface, the pressure would be equal to p naught plus dgh. Similarly, as you go more and more down, the pressure would keep increasing and increasing. So you will get more and more pressure. So actually, there is a very simple explanation also. Like suppose if someone is sleeping here. Now you consider water as a layers of fluid, right? So take an analogy with the blankets. So suppose if someone is sleeping here, so I am putting the blankets over him. First blanket, second blanket, third blanket, fourth blanket. So more the number of blankets you will put on him, the more he will be getting angry on you, right? Because he's getting more and more pressed. All right. So if one person is sleeping over here, so as compared to this person is more getting the pressure, right? Because this person who is at the bottom is getting the more number of blankets. That's why the more pressure on him. Similarly, the more number of layers above that particular place for the fluid layers, hence the more pressure. And when you go above the Earth's sea surface, it decreases basically because H will be negative in that way. Okay, so that's the variation of pressure with depth. Simple question we can try. Suppose there is a container, atmospheric pressure is P naught. Now the value of atmospheric pressure, if you don't know, let me just write here in terms of Pascal. Okay, I think I forgot to mention you the unit of pressure here. Pressure is force per unit area. So we can write it as Newton per meter square. Or it is also known as Pascal. Newtons per meter square is also known as Pascal. Okay, that's a short. That's another unit for the Newton, right? For the pressure. Now, similarly, if I talk about this question here, so here we can see the atmospheric pressure is 1 atm. Now, basically, how much is 1 atm? It is 1.013 multiplied 10 to the power 5 newtons per meter square or Pascal. Okay. Now, let's say in terms of P naught only we have to answer. We want to calculate pressure at this point. And let's say this height is 10 meter. Gravity we can take as 10. This liquid we can take as water, which is having a density 1000 kg per meter cube. It's a water liquid. So now what I should say? To calculate the pressure at this place, I must write P naught plus dgh. P naught is nothing but 10 to the power 5. We can use a 1.013, we can use at 1 only, approximately. 10 to the power 3 multiplied 10 multiplied 10. So we'll get this as 10 to the power 5 plus 10 to the power 5. So total pressure you're getting 10 meter below is 2 multiplied 10 to the power 5 Pascal. So when you go 10 meter below the sea surface, it will become just double, right? If the density you assume as 1000 kg per meter cube. So that's what the meaning of pressure. I hope you have understood what is the concept of variation of pressure with depth. Now let me begin with the concept of buoyancy. Now this buoyancy is a very beautiful concept, right? Because here I'll talk about now, if you have an object and if you place that object inside a liquid, then this liquid will float or will it sink? What will happen? So here, this idea you'll be getting from buoyancy. Buoyancy, or you can also call it upthrust. You can also call it upthrust. Both has the same meaning. It's not something new, first of all, right? This is just observation, right, which will be helping us to calculate whether the body will float or not. Fourth is basically buoyancy. It is a net force exerted by the fluid on any object. So net force exerted by the fluid. So while calculating the buoyancy, don't count into the picture the gravity and all. Gravity would not count, right? So because the buoyancy is a force exerted by the liquid only, so that's how the buoyancy has been defined. Okay, so do not count the gravity and all in the buoyancy. Only the liquid force we have to count. So you can see on the right hand side there is a picture. This wooden block, right? So depending upon the density, it may fall or it may sink or it may float there. So why the density term I used here? Let us try to understand. So first of all, let me calculate net force exerted by the liquid. Symbol I'll be using as B here for buoyancy. Let me take one container. And in this container, I'm going to place a block. And let's assume that this block is floating. Now, when somebody uses the term flotation, they're floating, what you should understand is the body is in equilibrium. If flotation is said in the question, that means body is in equilibrium. Right? Equilibrium means net force is zero. Okay. So that's a floating body, right? So net force is zero on it. But I just have to focus on liquid force. Okay. So how much force is exerted by the liquid on this body? Let us calculate. So from the bottom side, there is a pressure. From the upside, there is a pressure, atmospheric pressure, right? And that much pressure must be exerting the fluid also. So if you look at this red color block, then on this red color block, the total force which must be acting is this way. Let us write it. From the bottom side, let's say this height is how much? H in. I'm writing H in because this is the inside height I'm taking, not the complete height. Only the height which is inside the liquid that I'm taking here. Okay. So this pressure must be, let's say, some value P, right? This is the surface. So when you go H in depth below the surface, the pressure is P equal to P naught plus dg H in, right? Okay. Only inside height I'll take. I'll not take the entire height now. Entire height may be some H or something. Okay, this entire height can be H, but I have to take only inside height because pressure must be acting P naught plus this height. From this side, what is the liquid pressure? P naught. So multiply with area. Why I'm multiplying with area? Because I have to calculate the force. So multiplied with area. So that is the force. Pressure into area. So pressure written, force written. So now what is the net force? Now net force will be equal to the buoyancy because it is the only force from the liquid. So this force is upwards and this force is downwards. And when you see carefully, this force must be greater. If I call this as F1, F2, this as F1, F2 is greater than F1 because there is an extra term here, dgHn. And it should be because there is a more pressure at the bottom. So what I'll be mentioning here, that P naught plus dgh multiplied area minus F1 is P naught into area. Open this first bracket, P naught into area. Let me write it here. So net force, which is equal to buoyancy, only the liquid force. Don't count gravity right now. So P naught area minus dgh in into area minus P naught area. These two terms will get cancelled out. So buoyancy will be equal to dgh in into area. Now, what is height inside into area of cross section? The volume inside. And here you get the buoyancy as B is equal to dgh inside multiplied area, and which is nothing but equal to dg v inside, right? So that's what the buoyant force is. So what is d? D is the density of liquid. It's density of liquid, not the density of body. Always remember it. D is the density of liquid, right? Because here you see, I have taken P is equal to P naught plus dgh. And in this, what is D? Go back. What was D here? Density of liquid. The cylindrical thing was just an imagination, right? So do not get confused. So this D is just the density of liquid. So basically, that's the value of buoyant force. So buoyant force depends upon the density of liquid, right? We can mention here. It will depend upon the density of liquid density, not the object density. And it is equal to the volume inside. So now let me take 2 or 3 cases. Case number 1. So if you go back here, you see that net force on the body due to buoyancy is coming upwards. That's why it is called the upthrust. And another force must be the gravity, right? So if I see it carefully, if buoyancy is equal to total weight of the body, we'll call it what? We will call it a flotation, that the body is floating. All right. And now let's say, suppose if I take a situation where I am representing the mass of the body as density into volume. So buoyancy is equal to this. How I can represent the mass of the object? I can write it as density of the object multiplied volume. Density of the object multiplied volume. That's how I'm writing the mass of the object. Now, you see one thing. What will be the mg then? Mg will be equal to d object, volume of the object, total volume, because that's the total mass I'm writing, into gravity. Now you notice one thing. I'm going to compare these two situations. So this was the block, buoyant force acting in the upward direction, and the gravity is acting in the downward direction. If you see carefully, then the buoyant force is going upwards, right? And the gravity is acting downwards, right? Okay. If I'm saying that this is the gravity value, density of object multiplied total volume multiplied gravity, and this is equal to the buoyant force, d of the liquid gravity multiplied total volume. Now actually here the main part is density. So you imagine a case when you take the density of object greater than density of liquid. So when density of object is greater, you will see that the bottom term is more. It is dominating. So if density of object is greater, so the downward force is more. The gravity will dominate and the body will sink. Yeah. If density of the object is greater than density of liquid, the downward term will be more and the body will sink. In contrary to that, if I take density of object as less than the density of liquid, then the body will float. And now if the body is floating, as I've shown in this much in this figure, what is the height inside this? That we can calculate that by just equating them with each other. So here you just see that this is the case when the density of object is less than density of liquid. So body will float, and float means some equilibrium. Equilibrium means the upward and downward forces are more. So d liquid multiplied gravity multiplied v inside is equal to d object multiplied gravity multiplied total volume. Gravity will get cancelled out. So total volume of the object which is inside is equal to d object divided by d liquid multiplied total volume. That's how we get the total volume inside, right? So that's a way. If the body is having a more density than fluid, it will sink. If the body is having less density than fluid, then it will not sink, it will float. Then how much part of it will float? From here you can calculate. Let us understand this thing through a one question. So let us see this question. It's a very good question. Two bodies of P and Q of same volume float in a liquid. P floats with half its volume. So for P, the volume is its original volume by 2. Let's say the original volume of P and Q is VV because they have the same volume. And for Q, it is again half. Sorry, 1/3 of its. So P floats with half its volume immersed, and Q floats with 1/3 of its volume outside the water. So what is inside? 2V by 3. 1/3 is outside, so 2/3 is inside. So inside I am writing here. This is the inside one. Calculate the ratio of densities. Okay. So what to do? Both bodies are floating. So their weight must be equal to their buoyancy. So for the first body, what is the weight? Mass into gravity is equal to buoyant force. So density of liquid, right? Multiplied volume inside the liquid, which is V by 2. I'm writing for the body 1, P, multiplied gravity. How can I write M1? This is the buoyant force, guys. Density multiplied volume inside multiplied gravity. This density is a liquid density. This left side is the gravity force. M1 I can write as density of body 1 into total volume is equal to dVg by 2. Equation number 1. Similarly, for body Q, what I can write? Total mass is equal to dV by 2 multiplied gravity. Mass I can write as its density into total volume into this. Just remember, in the gravity, you have to calculate the total mass. So that's why I'm putting the total volume. But in buoyancy, you have to just write the inside volume. Now you divide the equation 1 and equation 2. You'll get the answer. That's it. So when we divide the equation and equation 2, see on the left hand side what I'll be getting. In the left hand side, d1Vg divided by d2Vg is equal to dVg by 2. Oh, sorry, it was 2V by 3. Sorry, my mistake. This was 2V by 3 for the second body. Total volume. 2V by 3. Okay. Yeah. So now I'll be dividing them. So dVg by 2 multiplied 2 dVg by 3. So that will go in the numerator. Now dVg and dVg will get cancelled out. Hence I'll be getting d1Vg. Okay, d1Vg also getting cancelled out. So no need to write that also. d1 by d2 is equal to 3 by 4. So that's the ratio of their densities. That's it. Just check the calculation mistake if there is any. I think we have made everything correct. So density into total volume inside, which is 2V by 3. And because of that, we'll be getting on the right hand side 2V by 3. Now we divide these two equations. So we'll get dVg by 2 and 2 dVg by 3. dVg got cancelled out and 3 by 4. And left side, these two terms got cancelled out. So d1 by dt equal to 3 by 4. That's it. Now there is so that's the concept of flotation basically. So if density of the object is greater than liquid, it will sink. Just remember this. If density of object is lesser than liquid, it will float. Let us talk about one more small concept. It's a very just formula I wanted to tell you. One term in physics called the relative density. So what is relative density? Small symbol I can use RD. Density of object. Now let's say you have five materials. Material 1, material 2, material 3, material 4, and material 5. And you have another material here. So now if you want to compare which material is more denser as compared to this, you want to compare all of them. So basically this is like your reference material. So how denser this material 1 with respect to m, how denser this material 2 with respect to m, how this is more denser or less denser with respect to m. This idea you will get from the relative density. So basically what do we get from the relative density is that how denser the object is with respect to the density of reference material. That's it. So here how you would be comparing it. So you will be writing density of m1 divided by density of reference material. You want to compare M2, just write down density ratio of M2 divided by M. There won't be any unit for this because it's a ratio of same physical quantities. So it's unitless, dimensionless. Now, suppose if you want to compare density of mercury, so relative density for mercury, Hg, which we use in thermometer. So mercury's the density is 13,600 kg per meter cube. And water density is 1000 kg per meter cube. Okay. So you can see the mercury's relative density is 13.6. Sorry, ratio won't be there. So 13.6. So that's the meaning of relative density. I hope you have understood this idea that what is relative density. It's just to compare how heavier or how denser the object is with respect to the reference material. So select the reference material. It is also known as the specific gravity. So that's it. So that was about the chapter called pressure. You have got a very good idea now about the buoyancy and all, how to do the calculations. Now you must solve some questions because that would give you the more better idea now. How to solve the flotation questions, how much part is sink inside, floating, how much part is outside, and then you will be solving some Olympiads level questions. Okay. So that's all from my side. Thank you so much, guys. If there is any question, just put it on over the PDF. Okay, then. Thank you so much, guys. Bye bye.